Okay, let's dive deep. We're looking at something pretty fundamental today. How can two people talking over a channel anyone could be listening to somehow agree on a secret key, a key that only they know?
Exactly. And that's the puzzle we're tackling using these Diffie-Hellman implementation criteria you mentioned.
Right, the sources we have here, they seem to lay out the whole process, the variables, the
Yeah,
calculations.
and importantly, they include sample data. So you can actually see the numbers working step by step.
So our mission basically is to unpack how this criteria demonstrates that process, how two parties end up calculating the exact same secret value securely just by following these mathematical steps.
Mm-hmm. It's less about the super deep number theory behind it today,
Yeah,
and more about walking through the practical implementation shown here.
got it. So where does the criteria say they start?
Okay, so it begins with establishing some public values, things everyone knows. There's a base number, let's call it A, and a prime modulus B. These are totally out in the open.
Public knowledge. Anyone listening in sees A and B. Okay, but surely they need something private.
Absolutely. That's critical. Each person, the sender and the receiver, chooses their own private secret number. The source calls them N for the sender's number and ARN for the receiver's number.
And these are the crown jewels, right? They never share N's or R's.
Never, ever. That's the bedrock of the security. They stay completely private to each individual.
Okay, secrets stay secret. So what do they exchange publicly then? How do they start talking?
So here's the first clever bit of calculation. The sender takes that public base A, raises it to the power of their own secret N's, and then, crucially, applies the public modulo B.
Okay, so A to the power of sten, then modulo B.
Right. The result of that calculation, as hewn percent B, that becomes the sender's public value, which the source calls SB.
And the receiver does the parallel thing.
Exactly the same structure. They take the public A, raise it to the power of their secret N, apply the public modulo B. That gives them ARN percent B, which is their public value, RP.
And these values, SP and RP, those are what they send to each other over the potentially insecure channel.
Precisely. They exchange SP and RP, so an eavesdropper sees the original A and B, and now they also see SP and RP.
But crucially, the eavesdropper doesn't see the DSEN or ARN that were used to create SP and RP.
Correct, and that's the gap.
So how do they get to the same secret key K from different starting points? Because the sender has SP and the receiver has RP. This feels like the magic step.
It does feel a bit like magic, doesn't it? But it's the elegance of modular arithmetic, which the criteria demonstrates. So now the sender takes the receiver's public value, RP, that they just received.
Okay, they take RP.
And they raise that RP to the power of their own private secret, answer P, and again apply the public modulo B, so RP and send per speed.
Right, using their own secret on the value they receive and the receiver symmetrically.
You got it. The receiver takes the sender's public value, SP, raises that to the power of their private secret, RMN, and applies the same public modulo B, that's SPRIN percent B.
And the amazing part, according to this criteria, is that RPSN per CB and SPARN per SPIN B, they actually compute to the exact same number.
That's the core mathematical property Diffie-Hellman relies on. They must result in the same value. And that identical number is their shared secret key, K.
Wow, okay. Even though they started the final calculation with different public values, RP versus SP, using their own private exponents, and that common modulo B brings them to the same secret endpoint K.
Exactly. And for an eavesdropper who only has A, B, SP, and RP, figuring out NSIN or RN is computationally very hard. That's the discrete logarithm problem. So they can't easily compute K.
Okay, so they've established K. The criteria then shows how it's used, right, for actual communication.
Yep. Once K exists on both sides, they can encrypt. The criteria example uses a simple XOR operation, which is quite common. If you have your plain text message, say P.
Like a letter or a number.
Right. You calculate K XOR P. That gives you the encrypted value. Let's call it E.
And because XOR is its own inverse, the receiver, who also secretly knows K, just takes the received E and calculates K XOR E.
And they get the original plaintext P right back. Simple, effective once you have that shared secret K.
The sample data in the source really nails this down. It uses actual numbers. What were they? A1787, B77R3.
And the secret's SN83001 and RN12566. You see SP calculated as 6256 and RP as 7670. Those are exchanged.
And then the final step, the sender calculates 76708, Deborah 08001%, 7703, and the receiver calculates 625612566%, 7703.
And boom, Both calculations, as shown in the data, result in the identical shared secret K38852.
It works, and it even shows the XOR part, plaintext P65.
Yeah, KXORP is 3852 XOR 3970, which comes right back to P65. Perfect round trip.
It just validates the whole flow described in the criteria beautifully.
So let's pull it together. The real achievement shown in this criteria is how two parties, starting only with public information and their own private secrets, can perform these specific calculations, exchanging only derived public values.
And mathematically guarantee they arrive at the exact same hidden shared key K without ever transmitting K itself.
And that shared secret K, as the sample data confirms, then enables secure communication using methods like XOR to encrypt and decrypt the actual messages, like recovering that plaintext P65.
It really is quite elegant when you see it laid out. Deriving a shared secret purely through mathematical steps, making eavesdropping so difficult even if the communication itself is public. Makes you wonder, doesn't it? What other secure exchanges you rely on every day might be using similar, clever mathematical principles just beneath the surface.